Yes. Thank you, Nick. So, welcome all our ISPRS and ISRS members and all the scientific community. Today, we have joined for the next webinar of our this webinar series on hydrosphere and
So as Praveen has frozen.
Yeah. Actually, it's raining in Dehradun. So,
Dr. Vaibhav,
yeah.
is it all? Is it everything fine?
Your voice was not audible in between. Can you introduce once again?
Okay. So I will start again. Dr. Paul Fellow, IEEE, received his BS and MS degree from University of Pennsylvania, Philadelphia, US in 1981 and 82 respectively, and PhD degree from Stanford University, US in 19.
Maybe Dr. Paul Rosen can introduce himself, might be quicker.
Yeah, I can do that. So good evening, good morning, good day to everybody on this webinar. My name's Paul Rosen. I work at the Jet Propulsion Laboratory, California Institute of Technology in California. As Dr. Praveen was saying, my educational background is a bachelor's and master's degree from the University of Pennsylvania many years ago, followed by a PhD from Stanford University.
Hello.
In radar remote sensing.
Am I audible?
Yes, I'm introducing myself.
Yeah, Dr. Paul has started introducing himself, and he will start the presentation. Actually, your internet is unstable today.
So I've worked
Paul, please.
Yeah, sure. I've worked at Jet Propulsion Laboratory almost my entire career after a couple of years as a research associate in Japan. And I focused on radar systems, radar engineering, and radar interferometry in my discipline area. I had the privilege to work on the shuttle radar topography mission, which many of you probably have used data from in the past. So today my talk is going to be about the NASA ISRO Synthetic Aperture Radar mission, NISAR, which is a partnership, as the name implies, between the NASA and the Indian Space Research Organization. It's been going on as a development for over 10 years now, and we are getting ready to launch very soon. And my topic today is to cover the hydrology and cryospherics discipline areas for NISAR. So without further ado, I'm going to share my presentation and get started. This is a picture of Jet Propulsion Laboratory and in a very beautiful time of year in the winter time. So we'll start with an animation of what NISAR the mission is. It's a little bit slow, so I'm going to probably speed it up here. So let's get started. We are launching our satellite from India. The satellite is, as you will see, a large, complex development, equal partnership between NASA and ISRO. We're launching on the GSLV Mark II launch vehicle, an Indian launch vehicle from Sriharikota launch facility in India. We're using the 4-meter fairing, inside of which the NISAR spacecraft will be stored in its stowed configuration, and we will launch at 6 p.m. on some night in the year 2025, hopefully as early as possible. This is, let me just speed it up a little bit to save some time. There's the launch. And then after we get into orbit, this is a NISAR spacecraft. First, we deploy the solar arrays. You can see this stowed reflector. It's a 12-meter diameter reflector on a 9-meter multi-part boom, which has to fit inside that fairing. Very complex engineering development, which we've spent many years perfecting, and one more 6-month period to go before we launch. You'll see the deployment coming up very shortly. A very complex set of maneuvers. In fact, here first we release the reflector. It comes out, and one of the hinges then activates and locks into place, followed by the second hinge, followed by the third hinge, and then followed by the final hinge. After the full deployment of the boom, there is what's called the bloom of the reflector that you can see right there. And this is a 12-meter diameter surface when it's fully deployed on a 9-meter boom with all of the radar electronics housed down here. As you'll see, there's 2 radars, one built by NASA, one built by ISRO. So NISAR in its fully deployed configuration like this will be making unparalleled measurements of all the Earth's land and ice-covered surfaces, and it will have unparalleled capabilities for almost all disciplines that it's designed for, including hydrology and cryosphere. And I'll try to make that point in this talk. I hope you can see the entire screen. Some of it is blocked for me. If you're having trouble, please let me know. But NISAR, we like to say, it will provide reliable, comprehensive products for science and applications across the globe. It's designed primarily for a number of specific science disciplines, which are illustrated here. You can see a picture of Greenland. We are interested in ice sheets and sea ice and their role and impact on climate change. We're interested in global forest cover and agricultural cover and how the carbon exchange between the atmosphere and the Earth are controlled by changes in that forest cover. And we're also interested in earthquakes, volcanoes, and other natural hazards which affect human populations around the world. These are our prime 3 science objectives that we have specific science requirements for that drove the design of the mission. In addition, we're also very much interested in the dynamics of water, hydrocarbons, and sequestered CO2 in reservoirs. So it definitely has a hydrology aspect to the mission as well. Our main attributes is that we're in a 12-day exact repeat orbit, taking data on all the ascending and descending passes of the satellite, and we cover all of the land and ice. So we get these global analysis-ready data products that are geocoded, terrain-corrected, polarimetric, and interferometric. So this is unprecedented in many ways. So for those of you who are not familiar with the techniques, this is just a cartoon figure illustrating interferometry. The idea for interferometry, which is one of our main measurement techniques, is we make multiple observations of a surface over time. So we fly over the surface on one day and measure an image. Another day later, the second pass, 12 days later in our case, we'll make a second image. And by interfering these 2 images in a coherent sense, we can measure the displacement of the surface down to a fraction of a wavelength precision. So here you can see from one time to the next, if the Earth moved by some amount of a wavelength, we can measure that quite precisely. And you can see here an image which is the relative change of the surface from one time to the next, sort of like a contour map of change. Because we're going to be measuring this comprehensively, we'll be measuring things in a swath that's 200 kilometers wide along the line of sight. We'll be measuring these things and we'll get hundreds of images over the life of the mission, so we can measure these changes in a sort of time series movie-like fashion. Good for measuring ice sheets, glaciers, aquifers, snowfields, and all kinds of solid earth natural hazards. In addition to the interferometric measurements, we also make polarimetric measurements. Polarimetry is good for understanding the dielectric properties of the surface as well as the geometric orientation of the surface. And you can see by combining a horizontally transmitted, horizontally received channel with a vertical channel and a cross-pole channel in different colors here, we can see very, very distinct scattering properties of these natural and man-made surfaces, where some colors, the bluer colors, indicate vertical scattering predominantly. The red colors are horizontal. The brown colors would be a combination of those two, and the green color would be the cross-pole signal, which is related to vegetation. So this cross-pole signal is extremely important for understanding the kind of vegetation we might see on the surface. And here you can see a list of all the many disciplines that benefit from these kind of polarimetric observations. So to summarize the observation strategy for NISAR, we have this table here. We have two radars, as I mentioned before, an L-band and an S-band radar, two different wavelengths, 24 centimeters, which is sensitive to larger scale scattering objects like tree canopy and branches and trunks. And we have S-band, 9.4 centimeter wavelength, which is more sensitive to slightly smaller structures. So by having these two wavelengths observed whenever they can observe together, mostly over India, surrounding regions, and Antarctica, we have an exquisite extension of the dynamic range of both our interferometric as well as our polarimetric measurements. So better sensitivity to all scales of vegetation. We have a unique design with this reflector and feed. Maybe you haven't seen a SAR that looks like that before. It allows us to get a 240 kilometer swath with full polarimetry if we need, in a 12-day exact repeat over all the areas of the Earth. So it's quite a capable system. Variety of resolutions. Nominally, we're at 5 to 10 meter resolution most places. And the life of the mission is planned for 3 years on the NASA side, 5 years on the ISPRS side. But if everything is successful, after 5 years, we will continue jointly together as long as the mission is successfully operating. We have designed this specifically for interferometry, so we have excellent pointing control and orbit control. And we have a very large duty cycle, especially at L-band, meaning we can observe all the land and ice at L-band pretty much all the time. We focus our S-band observations over India and Antarctica, as I mentioned before. And another unique feature of this system is that we look towards the left side of our velocity vector, which means that given our orbit configuration, we are looking much more at Antarctica than we are in the Arctic. The Arctic, we have a fairly large polar hole, so we don't see much of the sea ice up there. But we know that Sentinel-1 and other systems are focusing on the Arctic. So by looking to the left, we have this unique ability to capture the dynamic changes of Antarctica. So I mentioned several times that we have a very comprehensive plan. This is a cartoon of what our coverage plan looks like. So these different colors indicate different radar modes. I'm not going to spend too much time on that today, but you can just see that this plan, this coverage plan is imaged everywhere here, every 12 days from the ascending and the descending parts of the orbit. So average access time is around 6 days. And this is done every cycle for the life of the mission. One feature is that this is a science team driven plan, but we have a large science community who may have ideas about how they would like to see this changed. So we do plan every 6 months to update the plan according to science community input. We're hoping to get very continuous time series everywhere. So the changes to the plan, we hope, will be consistent with that time series approach. The products are, I think, at least to date, quite unique in that we have produced, or we will be producing not just radar imagery the way most missions do, but we'll be producing an entire suite of global level 2 products. These kinds of products do exist in the world, but no mission has decided that they're going to produce them globally so that users can effectively get these analysis ready data products directly and use them for their value-added science processing or applications processing. In particular, at level 2, we have what we call the geocoded single look complex image, geocoded SLC. This is basically the traditional range Doppler image that you typically see for a SAR image projected onto the ground as a complex data product. This is becoming a standard. Many people are starting to use this instead of the former standard product, and this allows you to read it directly into standard software and do your time series analysis with it. Similarly, we'll be producing interferograms globally. These will be in the range Doppler domain by science team request, but also there will be a geocoded version of these things. And those will be available again globally for all areas. So these interferograms, of course, do exist in software around the world, but we don't have global products like this that NISAR will be producing. We also have an interesting and unique way of operating the radar. It's an 80 megahertz bandwidth at L-band. That's all we're allowed to operate at, which gives us something like 2-meter resolution in the slant range direction, or 5-meter resolution roughly on the ground. We typically operate this sparingly because it takes a lot of data rate, but we often operate in this 40 megahertz mode and in this 20 megahertz mode. So the resolutions of these products are coarser, but you'll note this other band at the side here, a 5 megahertz band. This is a lower resolution mode that is used primarily as a way to correct for ionospheric delay artifacts. So that allows us then for each observation to make 2 images, one at full resolution and the other at lower resolution that can also be used. These are the postings. I won't go into those since we'll run out of time if I spend too much time, but this is what these products might look like. You get a full resolution image at, in this case, 20 megahertz bandwidth, so roughly a 10-meter product. And you also get this extra product at 5 megahertz that is separated in frequency somewhat, that can be used for ionospheric correction, which, assuming I don't run out of time, I will show you an example of later. The software that we use to generate all of these products is going to be open source already, so you're welcome to use it. Not all people necessarily will use the software, but the idea is that these tools are available to the community to use as they see fit. They can take them and modify them. They can contribute to them. And everything about the data products we produce is transparent and reproducible by the community. All of this will be done on the cloud. We have sample data products that are available at this website from our airborne platform, and our algorithms are published in these various websites. So now let me show you some examples of what we hope to achieve. These are from existing systems primarily. So doesn't really give you the full sense of what we will be able to achieve with these global observations over time, but hopefully it will give you a sense of where we're heading with this. So NISAR, as I mentioned, is designed primarily for solid Earth, cryosphere, and ecosystems science applications. And that means that we have a very specific set of observational modes and a very specific observation strategy. But we believe, because of the comprehensiveness of the measurements, it will be useful for any range of other disciplines. So we have global L-band data and regional S-band data. This is going to be great, especially over the places where we have both, for tracking, for maintaining high coherence and tracking large deformation signals as well as smaller ones. We have this split band design at L-band, which helps us to remove the ionosphere, which will clean up the measurements. I mentioned we're left looking, which complements the international constellation. So it's a unique measurement in that sense. And we get these consistent measurements, and they're all free and open. All the products are freely and openly available. Because we have this comprehensive plan, we'll have time series. And Sentinel-1 has showed us just the true power of time series. I think NISAR will complement Sentinel-1 greatly by adding to the temporal sampling as well as increasing spatial coverage because of the long wavelength coherence properties of the system. And of course, wide area mapping gives us high resolution synoptic observations for large scale and regional phenomena. So this is an illustration of why we believe L-band will really add to our knowledge of the Earth's surface in this fashion. There are L-band systems, the ALOS, the JAXA ALOS system, many people use. We use it a lot. It's a great radar, but the coverage plan has limitations and the data is not free and open always. So it can often be a challenge to create the kinds of products you would like. But you can see that L-band interferometry can get extremely improved, highly improved coverage of areas, particularly vegetated areas, compared to the shorter wavelength C-band measurements, because the long wavelength radar penetrates through the smaller parts of the canopy, which are moving and changing the scattering properties over time. So this is a great advantage, we think, for L-band. And S-band will be great too. So moving into some of the hydrologic applications, here's an example from our UAVSAR L-band quadpole airborne system, measuring a landslide over a place called some Slumgullion in California. The colors here represent the motion of the ground. And of course, there's some noise here and there, but you can see very clearly in this area of the landslide that there is a coherent motion of the entire hillside downward due to probably liquid moisture on the underside of this hillside. So having these L-band observations is very helpful in areas like this, which can be highly vegetated and moving quite fast. You can see here in Western California, using ALOS, many different passes have been used to try to search for landslides in the hillsides around California. Many of these are highly vegetated, and using L-band data, we can maintain coherence and be able to see these landslides and perhaps moisture effects related to them, which can help with modeling and understanding the risks associated with these landslides. Here's an example of a time series analysis of inundation. This one actually is from Sentinel-1 C-band. And we believe that the ability to discriminate water from land at L-band will be even better, especially for inundation, in that we can penetrate deeper through the canopy to see the scattering off the surface. Here's one particular image that's been thresholded to look for the boundaries of water. Inundated water. You can see the blue is the water and the yellow is not water. And this was imaged over many days using Sentinel, and this algorithm for tracking water and non-water was applied to look for inundation. And you can see very clearly the dynamics of the rainy season from this, understanding the hydrology of that area from an inundation perspective. So we expect this to work well, and we have specific science requirements for our L-band mission for global inundation mapping, as well as surface water extent mapping. Here's a great example from the Los Angeles basin showing deformation due to groundwater withdrawal over time. So this is over a period of years. And there's actually a sinusoidal signal. The LA basin is going up and down by about 2 centimeters every year. But in addition to the sinusoidal variability, there is this secular subsidence, basically compaction of the aquifer in the Los Angeles basin. This is seen in many aquifers around the world, and really is something that NISAR has opened many people's eyes to in terms of the impacts to local hydrologic systems. Here's another example of using NISAR to understand the deformation localization within the Central Valley of California, which is known to be subsiding very, very dangerously, shall we say. So what you're seeing here in the color is actually time, and it's color coded when the deformation signal has been noted. So this is uplift due to melting of snow in the mountains, recharging the aquifer in the Central Valley. So as time progresses, that water filters down through the valley, causes recharge and uplift in a time-phased fashion. And you can see how this correlates to the river systems and to the aquifer itself. And really it's really remarkable and helps people understand, the actual subsurface hydrology and aquifer design, shall we say, for future planning of aquifer exploitation. Here's another example. This is subsidence in Saudi Arabia, I believe, just showing that due to aquifer exploitation, there's plenty of areas here that are subsiding, and there is, I think, some oil pipelines that go through this area that could have an impact on critical, actually a railway system here, and here's the pipeline, just going right through the subsidence basin. So these signals that we can see with NISAR are not just for scientific research, they're also for practical applications. Moving to snow, one of our newer observations we're trying to understand how well we can do is snow depth change measurements using NISAR. In this particular case, what we're trying to do is use the phase difference in an interferogram, not necessarily to tell us how the surface moved, but to use the dielectric change to tell us how much snow has accumulated from one time to the next. And here's a very intriguing measurement that was done using our UAVSAR airborne system, taken 2 images at 2 different times, and then looking at the phase and converting that to a depth change through a model, comparing that on the right side here, or in the middle, to a LiDAR-based measurement. Basically, they scan the surface with the LiDAR at one time, measure the height, and then after the snowfall, they do another scan and measure the new height, and that tells them what the snow depth changed is, kind of like ground truth. And you can see very clear correlation between these radar-based measurements, based purely on the phase from the interferogram, to these LiDAR measurements. And you can see the correlation here is really quite good, surprisingly good. This is done at L-band, just the way NISAR will be for most of the world. There have been some experiments also with Sentinel-1, which is at C-band, shorter wavelength. You might expect it would not perform as well as L-band because the scattering properties at C-band might be a little bit more confused. But you can see the snow depth in the left column here with these 3 different regions, and the Sentinel-1 derived snow depth in the middle. And even though it's quite a bit noisier in the correlation, you can see down here in this table is not quite as good, it still shows a very nice correspondence. So even at C-band, you can get reasonable retrievals. At L-band, we can expect even better retrievals. And once we have time series of these measurements over a period of years, I expect we should really be able to do a great job at measuring snow water equivalent or snow depth change. Moving on to other aspects of the cryosphere, that was hydrology and snow. This is now moving on to ice sheets. So what can we do with NISAR in order to understand ice sheets? Well, we know the ice sheets are flowing continuously. They are snowed upon, ice forms, they accumulate mass, and then that mass is pushed out to sea. And we're trying to understand the dynamic relationship between the ocean water, the bed, lubrication, the surface conditions. All of that is a very complex system affecting our understanding of climate. So what we want to do with NISAR is measure as much of those things as are practical. We can't see the base. We can measure the surface velocity changes using NISAR, and we can measure grounding line. So here are examples of measurements from the cryosphere that have been made with past systems. These, of course, are from C-band systems primarily. Ascending and descending can be combined to create these global mosaics. With Sentinel-1, things have changed quite a bit. We have very good coverage these days of most of Greenland and the periphery of Antarctica. But more data is always good data, and NISAR will be making these kinds of velocity maps of Greenland up to about here, where we don't see above that latitude because we're looking towards the left. But we'll be able to make these velocity maps every month, basically. So not just velocity, but we can measure acceleration over the life of the satellite. And we get, as I mentioned before, excellent Antarctic coverage. So the goal is to make these kinds of velocity maps and measure not just the velocity, these stream flows, but looking at accelerations in this kind of context over time. This happens to be from UAVSAR measurements, again, from multiple directions. We'll get 2 directions for NISAR. So we'll get 2 components of the velocity, which should be great for measuring surface parallel flow. Oops. So what we do best is measure these dynamics. Here is a velocity map of Antarctica that was put together by colleague Eric Rignot many years ago, actually. And he had to use data from a variety of sources. You see in the lower left, it took him, I think, 10 years to put this map together, which means that there's many errors in it, and we don't actually measure the changes so much over time in the velocity. So with NISAR, again, we'll be producing a map like this every month or so. So we'll be able to animate this velocity map and its changes over time. Grounding line is an important aspect of understanding the changes in the ice sheet. Many people consider it sort of a thermometer for the health of the ice sheet. And the grounding line is where the ice goes from being grounded to floating. And because of the flexure of the floating part of the surface, you can see distinct patterns in the interferograms that allow you to measure where the grounding line is. And many measurements over time have shown that the grounding line is quite dynamic and has been changing over the years. But we don't have yet fully comprehensive measurements. And at C-band, it can often be difficult to measure. So we expect that the L-band measurements and the S-band measurements will definitely help in understanding comprehensively the changes in the grounding line and therefore mass change within the ice sheets. Sea ice is another thing that we would really like to understand in terms of its coverage and how it affects how the ice albedo and changes in the albedo will affect the overall insulation and heating of the oceans and exchange with the atmosphere. So you can see in the Arctic, the sea ice has been decreasing over the years. In the Antarctic, not so much, seems to be variable, but reasonably steady, although right now we're in a period of deficit. So this is very interesting, and our comprehensive coverage of the Antarctic sea ice will be extremely important for understanding this part of it. And we will combine what Arctic sea ice we get from NISAR with Sentinel to keep track of Arctic ice coverage. What we're trying to do is measure the motion of the ice. We're not going to get the central area of the Arctic, but we will get all of the motion in the Antarctic. We're looking at fracturing from the imagery, and we're looking at types and fractions of ice. And this we're going to be doing, I think, primarily with the L and S band together with polarimetry in Antarctica, collaborating with ISRO on that. So we use all different aspects of our mission to be able to measure these aspects of sea ice change. So here's some examples of measurements from past systems, probably from RadarSat, from colleagues at JPL, measuring deformation signals from one period versus a later period. And you can see that there's much more coverage earlier. Sea ice is decreasing over time. You can also use this to sort of measure the ice thickness distribution, and the distribution of leads and openings is very important for energy exchange. So we should be able to map that well with the system. Here's an example of velocity vectors or motion vectors that we can construct by taking images at different times and cross-correlating the images to see how much they've deformed and form these motion vectors, which give us these derived deformation products. So let me just go a little bit longer then. So we have this split spectrum band, and the ionosphere at L band can be quite a challenge. You can see this is an interferogram of a particular area. I don't know exactly where it is, but you can see a lot of color here, and that color is often due to the ionosphere. So we want to be able to remove those effects, and we use this split spectrum technique to be able to estimate the ionosphere, because the ionosphere is a dispersive signal. If you have two different frequencies, just the way GPS behaves, you can distinguish which parts are dispersive and which parts are not dispersive. So here's an example of an interferogram that is just a basic interferogram without any discrimination of the ionosphere. So it has both the deformation due to an earthquake as well as the ionospheric signal in it. Then we can estimate the ionospheric delay by combining split portions of the band and doing a calculation. This is now the ionospheric signal, and this is the non-ionospheric signal that's left after you subtract out this ionosphere from the interferogram. So you can see the earthquake. This is a very big earthquake, so you can see these fringes are effectively contours of deformation, and there's quite a big signal here. But much of that might have been interpreted incorrectly if we had left the ionosphere in there. So removing the ionosphere is quite important for these large earthquakes, and especially for very small ones. And this is true also for hydrology measurements that would rely on NISAR also. Just to give you a flavor for how much better we think NISAR can do, the previous example on the previous page was using the ALOS data, and the error in the ionosphere correction would be, up here for ALOS. I'm not going to discuss the units, but we are at least an order of magnitude better with NISAR down here. So then the noise level should be considerably better, and the uncertainty in the phase will be quite small after the correction for our measurement. So you can see here without split spectrum, no, that's never mind. Both of these are with split spectrum, but in one case we are splitting just the 20 megahertz or the 40 megahertz band. In the other case, we are using the extra band at the other end of the spectrum to do the correction. And you can see you get much better performance using the split spectrum technique. And here's just an example. These are of a time series analysis. These are interferograms over Southern California again, showing lots and lots of these signals, but these are all ionospheric signals. What we're looking for here is very subtle centimeter level changes in the position of the plates due to interseismic motion. There's also here geothermal activity and probably other hydrologic signals in the basin here. But the ionosphere is quite dominant in these things. After using the split spectrum technique, we remove all of that, and then we stack the images to create a rather exquisite velocity map of this area. With NISAR, this will be complete coverage pretty much everywhere, and the accuracy will be, an order of magnitude better for earthquakes, but also hydrologic signals and the cryosphere. We also have dense samples. We can use standard interferometric techniques, which are called distributed scatter techniques, or we can rely on permanent scatters, which could be like a rock, or it could be a building or something that's very bright compared to everything else in that pixel. And that gives us, these permanent scatters give us very good phase accuracy. So they allow us, if you just use those permanent scatters, you get often a good coverage, but if you combine the permanent scatters with the traditional techniques, you can densify the coverage very well. So we're developing techniques to be used with these data sets that combine permanent scatters with distributed scatters that help us unwrap and help us create more dense and complete time series. These are all from C-band data. Coverage at L-band should be even better than this. And we are looking at ways to use these data to understand even new signals. So here's an example of an analysis that was done in the desert where there is a dry lake, and this dry lake does fill up, or at least the subsurface of the dry lake does accumulate water, especially in wet years. And you can see right here, there's a hydro plant right here. You can see a clear deformation signature, but you can also see other variations within this dry lake here. And the question is, is this a real signal or not? Is there actually deformation or uplift in this dry lake? And the analysis was done to try to understand the relationship between precipitation and the measurement that you see over here. And so on this axis is plotted precipitation. On this axis is plotted the deformation signal in centimeters. And you can see that these precipitation events, which are down at the bottom here, which then accumulate to higher levels of precipitation, total precipitation, are very well correlated with these signals on the ground. So we can perhaps do a good job of estimating soil moisture from these time series as well, another hydrologic signal. So that's all I'm going to say today. I thought I would leave some time for questions. NISAR is in its final phase of integration. We were hoping to launch early this year, 2024. but there were some technical issues with development that caused us to reevaluate some of the hardware and try to fix some potential problems with it. And we are in the process of doing that right now in the US. This is a US piece of hardware. And we hope to ship that back very shortly and head for an early 2025 launch. We are producing these global products to level 2. They'll be fully and openly available to the global community through the Alaska Satellite Facility. So we expect that they will be extremely useful for both hydrologists as well as cryoscientists. We are placing all the data on the cloud. We're also placing all our tools and services on the cloud and hope that people will be able to exploit these data sets easily from that vantage point. So I think sort of the world is open for all kinds of applications. I think there are lots of exciting possibilities with this reliable dense time series over any site you care about. You can just draw a box on a map and say, give me this area, and you'll get those data supporting hydrology, cryosphere, and many, many other applications. So with that, I will stop and be happy to take any questions.
Thank you so much, Dr. Rosen. In fact, it was a very elaborated talk on the application of NISAR in, I think you have covered entire thing from cryosphere, hydrosphere, even the solid earth. And we all are very excited for the launch of NISAR. Even we are also looking forward for this kind of sensor. I think all our students, participants may get benefited by the sensor like NISAR. So if there, yeah, so there are.
I think you have now frozen. Vaibhav, you've now frozen. Is anybody else unfrozen?
Yes, I'm frozen. I can take it from here while they come back. Thanks for the presentation, by the way. I learned a lot.
Yeah,
there are
Nick,
a few questions for you. Yes. Okay.
Yeah, please coordinate the question and answers.
Okay. I'll take it from here. So we can we have a few minutes for the questions. We have a few questions in the chat box. Actually, one in the chat box, it says NISAR data will be tool will be like Snap software for ocean and land application with inbuilt algorithms.
Yeah, so the tools that we will be providing are not quite as integrated as the Snap environment. There's no GUI at the moment, although we're working on GUIs. It's mostly Python-based scripts that one can run that run these various algorithms. So it's not quite like Snap software in that sense.
Great. And then a follow-up question by the same person says, NISAR data, will there be any synergies with commercially available X, C, and L bands satellites or Sentinel mission?
So I don't know exactly what is meant by synergy in this context. Since Sentinel is freely available and NISAR is freely available, we already are using Sentinel all the time for all of our science analysis. And when L-band and S-band NISAR data are available, it will be absolutely fantastic to use them all together to understand what's happening on Earth. As an example, Sentinel is looking towards the right, NISAR is looking towards the left, and generally NISAR will get two lines of sight of deformation, Sentinel will sometimes also get 2 lines of sight deformation when they observe ascending and descending. Usually in global areas, it's only one direction, I believe. But any case, there'll be 3 independent or quasi-independent looks at a given point on the ground. So you can improve the accuracy of your 3-dimensional vector measurement by combining these systems where Sentinel correlates and where L-band correlates. So that's a great example of synergy. For commercially available data, of course, if you can afford it and get the data and they happen to image in the area of interest for you, it's the same kind of synergy. Generally, commercial data is more localized and higher resolution. So if you're looking for high resolution data comparable to what commercial provides, NISAR is probably not the mission for you. But if you're looking for something that gives you sort of, shall we say, synoptic coverage of a wide area that gives you context for your finer resolution commercial data, it would be a perfect way to synergize, I'd say.
Great, thank you. Another question by Surya Prakash. The question is, does the mission specifically emphasize crevices detection? Which technique is the most suitable to detect crevices? So I think glacier crevices, I think.
Yeah, I think for crevassing is probably you need a higher resolution system to see most of those than what we have for NISAR, I suspect. I'm actually not an expert on that, but I think probably you want to look at the commercial sensors, high resolution commercial sensors for that kind of application. There may be others on the call who know more about that than I do.
Great. We see if there's somebody wants to add. Otherwise, there is another question on snow depth measurement. So will NISAR in the L band, what is the depth it will be able to estimate? That estimate will depend upon wet and dry condition?
Yeah, so this is a pretty new area of research. I don't think anybody knows the answer to that question. But because we're measuring snow depth change from one time to the next, I imagine that if you have several feet of snow, you might have a difficult time measuring the depth. But if you are measuring a snowfall of a foot or so from one time to the next, and that accumulates from one time to the next, then you probably could build up the total snow depth over time. But I really don't think that we know the answer to that yet. There's very much a good deal of excitement in trying to understand what the limits of this measurement are. I think that's really where the research are.
Thank you. Sorry, always related to this, Surya asked, considering the leeward and windward sides of a snow-covered mountain and the extreme weather differences and other parameters contributing to changing weather and changes in snow water equivalent, does NISAR dynamically adapt and compensate for the electromagnetic wave absorption by water, EM wave absorption by water?
So the answer is no, there's no dynamic adaptation whatsoever. I'm not sure what we could do to dynamically adapt the signal, but the radar is fairly fixed in the way it operates. We transmit a fixed waveform. We have several waveforms to choose from, but I don't think that changing the waveform to different bandwidths would necessarily be useful in dealing with the changes that you have identified there. So we just take regular data, and I think the scientists will have to come up with algorithms that address the different ground conditions in different places in order to be able to interpret it. And it may not work everywhere. That's the beauty of research. We need to figure this stuff out. And we will have a data set that is comprehensive and reliable enough to be able to make definitive statements about how useful it will be. the only limitation is your knowledge of what's actually on the ground. So you have to design good experiments.
Yeah. Thank you. Questions? I think these were all the questions, unless Dr. Garg, Dr. Praveen, you have
One
other
more.
questions?
I think one more is there on the from Surya Prakash ji, whether the mission will specifically emphasize on the crevice detection.
Yes, we
Yeah,
covered those ones.
Okay.
Yeah.
Thank you so much, Dr. Paul Rosen, for taking
Hello.
your time late in the evening for this webinar. Dr. Praveen, would you like to add something?
Hello.
Yeah, you are audible. He is having very unstable internet today. Anyway, thank you so much. And Dr. Paul, we will also host your talk on the YouTube channel of ISPRS Student Consortium. So we'll take your consent for this. Yeah.
Sure.
Thank you.
Sure.
Thank you so much. Thank you.
Okay, you're welcome. It was my pleasure. Nice seeing everybody.
Right.
Oh,
Thank you.
Thank you.
Looks like there's another question here.
Oh,
Oh, really?
yeah. Would you like to
Yes.
answer?
Yeah. If SAR and optical sensors have to be integrated, optical sensors need sun synchronous kind of illumination. Does that affect SAR? Does it affect the SAR? I don't think that's what you mean to ask. It doesn't affect the SAR in any way, shape, or form as to how the optical sensor operates. But I don't think that's what you mean. I think, does it affect the interpretation of the SAR data combined with the optical data because the solar illumination conditions are different? I'm sure it does. In some sense, and you would probably have to apply some sort of a compensation algorithm to deal with the fact that the optical data may be taken at 10:30 a.m., which is typical for many sensors, whereas the SAR data is taken at 6 a.m. or 6 p.m. You might have to take that into account when you fuse the data in some fashion, but it really will be very dependent on the science target and what you're trying to derive.
Yeah, thank you. I think we have finished all the questions. It was really a nice opportunity to have you on for this webinar, Dr. Rosen. I think we should stop here as it's already
Just
late.
Dr.
Yeah,
Vaibhav, am I audible?
yeah, you're audible.
Yeah, so my connection was a little tricky today. So sorry for that. And just from my side, sir, once we have this NISAR in orbit and we have the main science objectives, will there be any follow-up mission to NISAR? Because once people start using the time series data, like we start using the Sentinel time series, people do get some kind of operational activities which are dependent upon these algorithms. So will there be follow-up or it is a standalone one-time mission?
Yeah, it's an excellent question. NASA had a plan to do a follow-on to NISAR, and we studied that for 5 years and came up with a number of concepts. NASA's budget is a little bit limited these days, and NISAR has been delayed quite a bit thanks to the pandemic and other issues. So right now, NASA does not have a definitive plan to do one after NISAR. However, that said, I'll say 2 comments. Number one, after NISAR launches and the data starts flowing, I think the entire mindset of the community and of NASA will change entirely. They'll see just how valuable the data are, and they will probably go rapidly to try to define the next mission. That's number one. And by the way, if ISRO wants to partner again with NASA, that might also help in convincing NASA. Secondly, the European Space Agency is funding the Rosen L-band constellation, which will fly together, 2 satellites fly together with Sentinel-1 in a 12-day repeat orbit. So even though we won't have continuous time series in our particular orbit, Rosen, assuming it behaves similarly to Sentinel-1, will have free and open data at L-band globally at 12-day repeat. Maybe not ascending and descending everywhere, but we'll see. I think Rosen has a lot of capability and many of similar objectives to what we expect from NISAR. So sometimes we think of NISAR as a test bed for what Rosen will do. And Rosen will launch sometime around 2028 to 2030. So just about the time that NISAR will be reaching the end of its design life. So.
Can I ask one curiosity now? Sorry if I jump before we finish. All of this SAR explosion that we are witnessing right now with these new satellites, new missions, especially also the spatial resolution is getting interesting, smaller, etc. And also different polarizations that gives us a lot of features. Does optical remote sensing still have advantages? Like, I'm an optical remote sensing scientist most of the time, but I'm getting interested in SAR because of all of this new mission, and I'm starting wondering. We used to have hyperspectral satellites, but if with SAR we can get down to 10 meters, and then multiple polarization can give us many attributes that we can feed our algorithms to. What is the future of optical?
I think they're quite complementary. You know, hyperspectral and even multispectral sensors are measuring the chemical properties of vegetation and ground surfaces. We're measuring dielectric and structural properties. So we're really measuring fundamentally different things. And even if you have a lot of data and throw a machine learning algorithm at it, I don't think you'll necessarily be able to derive the same things that you would from optical instruments. Certainly there will be things that overlap, and you could probably swap one in for the other. But I don't think everything. I don't think detailed geologic mapping, detailed plant health on a per frame basis will be as easily derived from SAR data as you would derive it from like a hyperspectral or even a multispectral system. Clouds are always a problem, and nighttime issues and all that stuff with optical systems, but there's so many of them coming online now that generally speaking around the world, even the cloud issues are not as much of a problem as they used to be. So I think there's always going to be a place for optical. They're quite complementary.
Thank you.
Yeah, thanks, Dr. Paul. Just one request: we need your permission to host this recording of this webinar in our YouTube channel.
Yeah, I think it's okay. I don't actually know what JPL's policy is about that, but I'll just say okay. And if you do it and I get in trouble, then you'll have to take it down. So it's probably okay.
Yeah. Thanks.
There's one comment that says I should have had more Indian examples. I do apologize for that. I have to say, I was on vacation recently and I got a lot of things to catch up on, and I wanted to include some examples, but I didn't have the time to interact with my Indian colleagues to get their permission to use their content. And I don't like showing other people's things without their permission. So I do apologize for that. There's plenty of good stuff from India. Praveen himself and others could provide that.
Yes. Smriti want to ask something. Smriti, you are online. Hello.
Yeah, hello, sir.
Yes, go ahead.
So just wanted to ask, like the algorithms which we are developing on Sentinel-1, would it be applicable? Means like we are kind of developing the algorithms right now for Sentinel-1, and would it be good to use? Yeah, definitely it will be good to use for the NISAR. So we are assuming that the data will be kind of similar to the ones which we are using, but certainly the bandwidths are very different. So do those algorithms will need a lot of changes or will be in the same regard?
It depends on which algorithms you're talking about. I think most of the geodetic related algorithms for measuring displacement or time series motion, those will probably be nearly identical because the same phenomenology occurs at both wavelengths. For if you're doing something like biomass derivation, those have to be calibrated to the wavelength because the scattering properties at the different wavelengths are quite different. So your algorithm could very well still be applicable once you go through a calibration phase. And for other things that are basically threshold detection, like surface water extent or inundation or vegetation, like agricultural area change, which are based on correlation differences. Again, I think those algorithms should be applicable once you calibrate with the right thresholds. So yeah, I think it should be fine.
Thank you.
You're welcome. Okay. Well, thank you very much for inviting me. It's always a pleasure to speak about NISAR. It's a little late here, so I hope I didn't sound a little bit less excited about NISAR than I actually am. It's a very, very exciting mission, and I can't wait for it to launch.
Right. We also understand that it's already late. So once again, thank you, Dr. Rosen, and we'll look forward for similar support in future as well. Right. Bye-bye. Good night.
Very good. Good night.